cause of many problems. Okay, so we left off on talking about our neural network, and so here are the notes, and we set this up, and we went through and we did our taking our derivatives, and taking derivatives we call back propagation, and so we ended up calculating. We found the derivative with respect to W2, okay, and the derivative with respect to W1. So here we got the derivative with respect to W2 as this, A transpose, and then our delta is going to be minus y hat f times f prime of z3, okay? That's our derivative with respect to W2, and then we expanded that to get our derivative with respect to W1, and we got this, okay? So we figured out our gradients, our derivatives, and when you apply the chain rule, that's what we call back propagation. And then now we are in the process of coding this up, okay? And so I've posted this code online, and so here we are. We take our input data, okay? So we have 3 pairs, x1 and x2. We have our outputs y, okay? And then we are going to scale our data so everything's on a scale from 0 to 1, okay? And that just helps in the processing of our thing. We said our input layer has 2 nodes, our output layer has 1 node, and our hidden layer is going to have 3 nodes. And then as far as our weight matrix, all we're doing is we're going to say it's going to be our first weight matrix is 2 by 3, 2 inputs, 3 in the hidden layer, so it's a 2 by 3. And then we went through basically the steps of forward propagation. We said we're going to take our inputs x, multiply it by the first weight matrix, that produces our z, right? And this is just going straight off of our notes. We're taking our x, multiplying it by our weights, and we get our z's. And then we apply our activation function. Our activation function is the sigmoid function. We can plot what that looks like. It looks like this, okay? And then so we apply the sigmoid function to the z to get our A matrix, our A2 matrix. That's what we have there. We create our second weight matrix, which is a 3 by 1. That's our W2 matrix. And we are going to multiply A2 by W2 to get our Z3, just moving right along. And then finally, we apply the activation function to Z3 to get our Y hats. Okay, and we can see what our Y hats are. Our Y hats are terrible estimates right now. Okay, they are no good versus our actual Ys. Our actual Ys are 0.75, 0.82, and 0.93. And so we can calculate the difference between our Y hats and our Ys. And so this is going to be our cost function or our loss function. And again, just for, we multiply by an arbitrary constant of 1/2. But effectively, all we're doing is we're taking the difference between y, y hat, we're squaring that, and we're adding them up. That's our total loss function. Okay, and so currently our total loss function is 0.0153. That's where we are. All right, and so now we want to implement finding the gradients. And so part of that is to find the, when we did our gradients, we found the f prime function. Okay, f prime we said is e to the negative z, 1 plus e to the negative z on the bottom squared, and that's all I've done. E to the negative z divided by 1 plus e to the negative z quantity squared, that goes on the bottom. Okay, so that's our sigmoid prime function. And in the video we can plot what this looks like. This is our sigmoid function. This is sigmoid prime. We can see there's the steep slope is the highest at its inflection point, which makes sense. Okay. And then, so to implement our gradient with respect to W2, it's going to be our A A2 matrix transpose times delta 3. Delta 3 is y minus y hat times f prime of z3. Okay, and so that's what we have. We got delta 3 is y minus y hat times f prime, which is sigmoid prime of z3. So I'm just coding exactly what we've come up with mathematically into R here. And then we're saying the gradient, which here we're calling dj dw2. This is the gradient with respect to the w2 matrix, is the transpose of the A2 matrix times delta 3. Okay? And so we've done it. Okay? So, you know, all the hard work here is really coming up with the math and figuring out exactly what we do. And then it's just putting exactly what we found in the math into code, right? And then so this is what we have. And if we, oops, that's not what I wanted. Okay, and then and I'm calling this delta 2, but it's all I'm doing is to find our gradient with respect to W1. I'm taking delta 3 times W2 transpose sigmoid prime or f prime of z2. Okay, so this is after all of the work in figuring out our derivative here. This is what we have, and we can see I'm taking our resulting delta 3, which we found earlier, multiplying it by W2 transpose multiplied by sigmoid prime, okay, of z2. And then I'm going to multiply that by the X matrix transpose, X transpose, okay? So I have X transpose times all of this, and that just, I could have put it on one line. I have it split on two, but that's what we have there. All right, is this okay? Taking everything that we've derived earlier, putting it into the code in R, and then so we have, these are the gradients as we've calculated based on our current values for W1 and W2, where currently my weights for everything is 1, which is clearly not going to be correct. Okay, and then so what we do for gradient descent is we just take our current value and then we multiply we just subtract off the gradient, right? We're taking a step in the direction opposite of the gradient. So we're just taking our current estimates, W1, and we're going to subtract off some scalar value times the gradient. Okay? And so we do that, and we do that, and then we update what our W1 values are. So this is after one step, this is where we are, and W2 after one step, this is where we end up. Okay? And then we can see, you know, what is the cost here. So the cost one is now 0.015, whereas the earlier cost function, oh, I have to scroll back a little bit. So when we first started off, our cost was 0.01532851. It looks to be, oh, I'm sorry, it's exactly the same, sorry, because this is using our current y and y hat. After we update all of this, okay, we can recalculate what our cost is. Okay, we're going to just do forward propagation, do x times w1, apply the activation function, multiply those results by w2, and then we get a new set of y hats. Okay, and our new set of y hat, these are our new estimates. And we can see, you know, are these estimates better than what we had before? Okay, previous our old y hats were this. Are these better? And so we calculate the cost function here. Cost 2, we can see cost 1 versus cost 2. Indeed, by taking by changing our weight matrices, by taking a step in the opposite direction of the gradient, we see our cost has gone down. Okay, so we did get some improvements here. Okay, so that's exactly what we want to see. If you watch the videos online, the author, and recommends doing something called numeric gradient checking. Okay, and I also agree, and I say this is a good idea. Okay, because a lot of times, you know, when you, especially when you're, you know, let's say after you graduate here, you find a job and you're working as a data scientist, right? Which is, you know, a great scenario. And then your boss tells you, you know, I want you to do this thing, and then you're not 100% sure how to do it, so you look up things online and then you try coding something up, okay? And then you try it out, and then you have this question, did I do this right? Is this working, right? And there's no answer. There's no one to come back and look over your work and say, oh yeah, this is correct, okay? This is your job now. You got to figure out, am I doing this right or am I not, okay? And so one way you can kind of answer these things is to go back and think of, you know, what exactly am I trying to do, and is the result I'm getting moving in that direction? So over here, one thing is that we're trying to reduce our cost function, and we succeeded in that, okay? Another thing is that if we think about the definition of the gradient is essentially a derivative, right? And so what we can do is we can go back and we can think of exactly the definition of the derivative and do a kind of a primitive check here. And I didn't hook up my tablet, but I'll do it. So if we think back, you know, what's the formal definition of the derivative that you learned in calculus? Yeah, let's see. Is this not working here? Okay, hang on. This always gets checked out. Okay, and so, you know, if we think of, you know, what is f prime of x, this is what we say is we take x and then we add a delta and then we subtract off what that is, and then we divide by delta x, and then we take this limit as delta x goes to 0, right? This is kind of what we are doing for the derivative. And so we can do something similar for a gradient, okay? Similar idea for the gradient. Okay? So we currently have some gradient matrix, or weight matrix W1, okay? W1 is a 2 by 3 matrix, okay? And we currently have some values in here. I don't know. Right now it's like 1, 1, 1, okay? And what we can do is we can add basically a little epsilon, okay? A little epsilon matrix, okay? And so what I'm going to do is I'm going to go ahead and calculate our current cost right here. And then I'm going to take a little epsilon, which is 1 times 10 to the negative 4. So like 1/10,000th of a thing. Okay? And so I'm just going to add a tiny little disturbance to this thing. And then we're going to see how much the value has changed. Okay, so I'm going to add I'm going to take our weight matrix, add the perturbation, or you know, just add this to each value here. We're going to recalculate all of our values, okay, and then we will see how that affects our current cost versus the actual cost. And then we can take divide the difference there. So, you know, we add this here, and then we go through the calculations. Okay. Okay. So then we you know, find the cost function, you know, with the new w plus epsilon. Okay, using this. Okay, and then what we're going to do is we're going to take the difference of the cost function using the original weight matrix and then subtract off the cost using the weight plus epsilon. Okay, and then we take that difference, and then we're going to divide by epsilon. Okay, and if we do this, then this should be approximately equal to our gradient. Okay, approximately equal to our gradient. So we can check this. Okay. Does that make sense? Okay, so that's what we're going to do. So I'm starting off. I'm going to create something called the numeric gradient. This is a placeholder to calculate all of our values. Okay, and so we have 6 values in our weight matrix. So what I'm going to do is I'm going to start off with the using the same weight matrix that I have up here. So I've got the starting weight matrix is using 1 for every single value, and I've got that's going to be W1, and I went ahead and I calculated the cost right there. And then we go through, and then for we have 6 values in that weight matrix, and so we're going to start by just adding an epsilon to just one of those values. Okay, and we see how much. We go through the calculation. Once we change that one value, we go through all the calculations to calculate our new predictions, new y hat, and we get our cost function of that, y and the y hat. And we compare that to the cost where everything is a 1. Okay, so right here, so I guess in the first iteration, okay, so for I equal to 1, all we've done is I've got 1.0001 here, and then everywhere else is a 1. This is going to be my W1 matrix, okay, is this. And then we go through the calculations, we go ... and we get our new y hats, okay. And then we calculate the cost between y versus y and y hat, okay. And so this is our loss function here. And then we compare that versus the cost between y and y hat, and over here this is where W is equal to just 1s everywhere. Okay, so that's all we're doing. And then that's going to be the numeric gradient for the first spot in our so the difference here, as we're filling out our delta L with for W1, this will, whatever this value is, this is going to go in the first cell. Okay, and then we go through and we do this for all 6. That's what we're doing here. Okay, so I've got for I in 1 through 6, this goes through the W1 matrix, adds 1, calculates the difference, creates a numeric gradient there. Okay, and then so here my numeric gradient for W1, this is its estimate of what the numeric gradient is at for W1 after doing it this way. Okay, we do a similar thing for the gradient of W2. Okay, I create a placeholder there. I go through and I perturb each value in W2. We recalculate our estimates of y hat. We take the difference there, divide that by the size of the gradient, and then we get values for what our numeric gradient of with respect to W2 is. Okay, and so we have that. I'm sorry, yeah, and then so we go through, we can calculate what the gradients are using the functions that we've designed, right? So this is not using our numeric gradient, but using what we believe to be the, after we've done all of our derivations, okay? And we can compare our numeric gradient values. So this is our numeric gradient by adding 0.0001. So this is what we have, so let me just do a quick comparison here. So we've got numeric gradient 1, and we can compare that to what happens when we plug in our numbers. And we see that these values overall look very, very, very similar, okay? And we can compare our gradient values when we did the using our derivatives versus when we calculated them numerically. Okay? And we see the values are also very close. Not exactly the same, but also very close. And so this would be an indication that using this method to calculate our gradients according to the kind of our calculus that we used, this is an appropriate way to calculate our gradients. All right, is that okay? So that's numeric gradient checking, and it's a good step to do to just kind of make sure that you're on the right track, or that you haven't messed anything up. Because that's always something in the back of your mind. When you code something up, you're always just like, did I do this right? And these are just some assurances. Okay. Another way is you can compare the norm of the difference divided by the norm of the sums, and that should also, they should be small values there. Okay. Okay. Over here, we are going to do the gradient descent. Okay. This is just plain old gradient descent, taking steps in the negative direction of our gradient. Okay. There's a few. Gradient descent is kind of this very basic method that works a lot of times, but also it can get stuck when the surface becomes flat, or it can get stuck, or it can not converge. There's all sorts of problems with it. There's something called BFGS, which is a method that tries to improve it. We're first going to just start off with ordinary gradient descent. Okay. So first, to do this, I'm going to first start off by just taking random values between 0 and 1 and creating my W1 and W2 matrix. So my W1, these are just random starting weights for the W1 and W2 matrix. Okay? And then to keep track of all of our cost functions, I'm going to create a vector called cost history. Okay? And we're going to go through and do gradient descent. So we're going to say for I in 1 through 10,000, we're going to take 10,000 steps. Each step, we're going to calculate the current cost and store that in cost history. Then we go through and we calculate the gradient at this point. And then once we've calculated the gradient, we just update our weight matrices by taking a step in the direction opposite of the gradient. Okay? And then every time we do that, we have to go back. We're going to recalculate our cost, recalculate our gradients, and take another step. And we just do this over and over and over again. So we're going to do 10,000 steps. And there, it's done. Okay? And then let's take a look at what our weight matrices are. Here are our final weight matrices after 10,000 steps of gradient descent. Okay? We can see what our predictions are at this point in time. Our y-hats are 0.749998, 0.8200548, 0.92989. Okay? Compare that to the actual y's of 0.75, 0.82, and 0.93, and we can see we've got pretty good estimates. Okay? After readjusting all of our weights, our new predictions y-hat is pretty good. Okay? If we can look at the cost, and our cost is on the order of 10 to the negative 9. Okay, so it seems like we've really minimized our squared residuals here. Okay, and we can see, we can plot the history of our cost function or our loss function here. Okay, so when we first started off with our random weights, our cost or our loss function was quite high, and in the beginning we got great improvement right away, okay, and then it kind of leveled off, okay, and it was just kind of searching around, and then finally it found another spot where there was a bunch of improvements, and then since there it's been kind of steady, maybe just barely improving here and there. Is that okay? And so there you go. That's a neural network, gradient descent. We've got our new weights trained, and then we can give it we can start off with a new set of x and then plug it in here to get kind of some new estimates here. So these are our current. This is what we have, and our y hats we see is this. And if I were to just plug in, let's call this x2 is, let's make a matrix and say we want to, say our inputs are 10 and 4, we can ask what are the what is it going to be, and so here we'll go through and basically apply everything that we had before, except now we're using our x2, and then so our y hats here. This is the estimate if I use 10 and 4, okay? And so we can plug in things that way. And go back and just reset what my x's are. Okay, so that was a lot of work just to get that. Okay, we can expand this to other things, and I think, well, maybe I'll introduce this in a little bit. I do want to say, so all of this gradient descent stuff we've done manually, right? We're saying we're calculating the gradient ourselves manually, and then we take steps in the opposite direction. This is all part of this overall umbrella topic of mathematical optimization. And R has some functions built in, okay? And there's an optim function here. And this implements a bunch of different optimization methods. There's the Nelder-Mead, BFGS, all of this stuff, other stuff that does this, and you can read up on each of these different optimization algorithms, okay? And so if we wanted to use that, we can use R's optimization thing as a way to optimize our cost function, okay? And so what you have to do, as far as the optimization function goes, you need to give it a list of parameters and then the function, and then it will do the rest. It will find the correct set of parameters to optimize the function, is what it's going to do. And so what I have to do is, currently our parameters exist in two matrices, right? We've got a list of 9 parameters, but 6 of them are in weight matrix 1, 3 of them are in weight matrix 2, okay? So as far as the function that we want to optimize, this is a function of, we can just give it just one set of parameters, W, but then I'm going to have to say the first 6 go to weight matrix 1, and then the last 3 go to weight matrix 2, okay? So this is just a way to say, give me a set of values. Here there's going to be 9 W values, and then what it returns is going to be the cost associated with those 9 values. So here I've rewritten so that we have just a vector of 9 values, and those 9 values get split into the 2 weight matrices, but the result of this function still returns back one cost function, okay, or one cost value. Does that make sense as far as what we're doing? Because if we want to use the optim with R, we need to have our functions specified in a certain way. Okay. And so we do that. We're going to start off with just 9 random values for our parameters. The function that we want to optimize is our cost function, okay? And then we're going to just say, do this. It defaults to using BFGS. We're going to say, just stop at 1,000, after 1,000 iterations, okay? And so there we go. That's it. Here are the results. Okay, And the resulting things here are the 9 values it found, and the value here is of the thing is on the order of 10 to the negative 11. Okay, we can take the resulting parameters. Okay, so it found 9 values here, and we can say, okay, well, we want the first 6 to go into weight matrix 1 and the last 3 to go into weight matrix 2. Okay, and so we could see what our weight matrix 1 is and what our weight matrix 2 is. Okay, and we can compare this, how did this work compared to our original function here? So when we did gradient descent, these were the estimates, and we see that they are kind of different. Okay, but that's okay, because this is a high dimensional data set, and so you might have similar solutions in different parts of the this 9-dimensional space here, and that's okay. But we can see how do our estimates go. Okay, and we can see what our y-hats are, and we see indeed the estimates produced this way worked out pretty well. Okay, these match the actual values of y very closely, and so this works as a set of nine weights that could optimize our function. Okay. One thing about all of these optimization methods is that if we start at a different location, so here I'm going to say set seed 10, and so all that does is it changes the 9 starting weights that I'm using for my vector of parameters. Okay, I'm going to just say run the optimization function. We run that, and I print out the results. Okay, this is the list of parameters. This is the value of the cost function. So compare that over here. The cost function after a lot of iterations was on the order of 10 to the negative 11, and over here at the end the cost function is on the order of 0.001, so it's like 1 in 1,000. So the cost function here, I would say, did not truly get optimized. Okay, and it also returns back convergence 0, basically saying it didn't really find a solution. Okay, and we can go back and we can see, what if I figure out my weight matrices based on these results here, and I print out my y-hats. We can see my y-hats versus my y, it didn't do a good job, right? It's predicting 0.75, but where the answers are 0.82 and 0.93, it's giving me back 0.853 and 0.893. Okay, didn't do a good job here, and sometimes that happens with just different starting sets. Okay, and we can kind of see, like, here's another thing over here. I ran it, and then I'm getting on the order of 10 to the negative 15. So that did a really good job. Okay, and again, we can kind of see what are the results there. Here we see the results here are very, very close to the actual results. So just different locations can give different results. Something happened. Okay, after 1,000 iterations, different starting location, it didn't find a convergence here. Okay, so that could happen. And here I'm just trying like 100 different starting locations and seeing how often it converged or didn't, and you'll see that it doesn't always work out as well as one might hope. Okay, is that all right? So this is a neural network, and this was a very simple one where we had 2 inputs, a hidden layer with 3 nodes in the hidden layer, and then 1 output node. Okay. So I want to introduce, and we're not going to really get into this, but there's a famous data set. Now this is now becoming a modern classic. So like there's classic data sets, right? Like Galton's data set on heights, and then like the Iris data set, and the MNIST handwriting digit recognition is a new classic. And so if you just go online oh, and you type in MNIST into Google, the very first thing that will pop up is this handwritten digit database. Okay, and when you go there, you can download these 4 files, and they're just in kind of this weird format. Let me close this poll here. They're just in a weird format, and so I'll post some code as far as getting this data into R, because it's a little strange, and I think a lot of people have done work into making it easier to read, but then they just become these huge files. Okay, but basically, you know, I think it's coming from the post office. Well, I'm not 100% sure where this data is coming from. But here's the application is, you know, you write an address on a thing, you got blah 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 blah. All right, and then down here you have a zip code, right? 90059 or something like that. Okay, what's UC? It's like 90095. Is that our zip code here at UCLA? Something like that. Okay, and so somebody. So as far as training data goes, somebody went through and they zoomed in on every single one of these and they parsed out exactly they made a little square, okay? And then so what the data consists of is you have these images, these grayscale images of 28 by 28 pixels, okay? So you got a 28 by 28 pixel thing, and then you have a digit written in there. So how do I get a fat marker tip here? Okay, so you might see something like this. Okay, and we want to be able to classify this, okay, into one of 10 digits. Okay, so this is our input. Our input is basically we turn this, the 28, into what's 28 times 28? I don't know. Almost 900, but 784. Okay, is a vector of 784 values, right? 784 being the result of 28 times 28. So you have 784 inputs, okay? And then what we want to do is our output is we want to classify it into either 0 through 9, okay? This input, okay? So don't even think of this as a picture anymore. It's just an input of 784 numbers, okay? We're just going to take the input of 784 numbers, and we want to classify this input as a digit. And it's either going to be 0, 1, 2, all the way up through, 8 or 9. Okay, we got 10 possible outputs. So what we're going to do is we're going to set up, this is a very primitive way, but it'll work, okay? Is we're going to have our input layer will have 784 nodes. Okay, 784 nodes. Okay, and then we'll have a hidden layer. Now we can choose an arbitrary number of nodes for a hidden layer. Maybe 150 nodes, okay? I don't know. Whatever you want, okay? Okay, so you're going to have this gigantic weight matrix that connects, every single one of these outputs or inputs to every single node in the hidden layer, right? You're going to have just this crazy weight matrix with going from 700. Your weight matrix will be 784 by 150. So it's a very large weight matrix. So your W1 weight matrix will be 784 by 150, okay? And then how many output nodes should we have? Okay, we're going to have 10 output nodes. Okay, so each output node will correspond to one of our digits. We'll have output node, we'll have 10 of these output nodes. This one will correspond to digit 1, this will correspond to digit 2, this will correspond to a 3, a 4, a 5, so on and so forth up to 9 and 0, okay? Or maybe I'll have 0 at the beginning or something like that, okay? And then so, and again you'll have another weight matrix that, you know, connects all of these, okay? So weight matrix 2 will be 150 by 10, okay? And then our training data, we're going to take each of these, and so our inputs, so as far as our training data, will be input of 784 values, and then the output will be, you know, if it's, let's say it's the digit 3, it'll be, you know, 0, 0, 0, 1, 0, 0 elsewhere, okay? However we code this up, okay? So we have to set up our training data that way, and we're going to have tons of input things and tons of output things, okay? And we're going to use that to train our neural network, okay? So we have a lot of weights to figure out, right? 784 times 150 plus 150 times 10. So we've got a lot of weights to figure out, but we've got a lot of data to help us guide there, okay? And so we'll do that on Friday. It gets complicated just because there's so many input things that we can't, to process all of them all at once is very computationally intense. So we're going to just we're going to do something called stochastic gradient descent, and I'll explain that on Friday. But this is a really neat application of the neural network here. Okay, we'll see some handwriting digit recognition here.